So let's get started with the class today. Okay? So we'll just forget about this one. I don't even know what the answer is supposed to be. Oh, let's look at motion of an ideal fluid. We'll come back. We'll see some other questions about this. Okay, can you repeat? Well, if you really wanted to make it right, you would have to have the object in a fluid, but yet it would have to be like tied down somehow to the bottom. Like I could ask you, what is the force that is required to hold it down? You want to do that problem? Is that useful? What? Did you say no? You want to do that? All right. We'll do some more practice with Archimedes' principle, okay? All right, let's look at ideal fluids, though. Ideal fluid, we'll look at a couple things with fluid flow, the equation of continuity and Bernoulli's principle, and then the, what's the other thing here? Oh, that's it. So a couple ideas about ideal fluids, and you just need to know these in name and know what they represent. First of all, an ideal fluid is non-viscous. That means that there's negligible friction between the molecules. So, pancake syrup, viscous or non-viscous? Viscous, right. Water, viscous or non-viscous? Non-viscous, right. There's a range of viscosities, but it's generally fairly obvious, at least the questions that I'll ask you, what's viscous and what's non-viscous. Incompressible. That means that the density is constant regardless of pressure. All right, so all liquids are basically incompressible. All gases are compressible. So far we're talking about liquids that are not viscous, they're not sticky, they're not thick. We're also talking about only liquids, not gases. Gases are an entirely different beast in dealing with how they flow through space. This means that, for example, if I have a container of a liquid, that though the pressure at this point is small, P1, and the pressure down at this point is big, right? Because P is equal to rho GH. As I go to a deeper depth, the pressure gets bigger and bigger. The densities at these places, P2, the density is going to remain the same. The density stays the same. This one is smaller, but these two are equal. Okay? Even though the pressure changes, the density remains the same. The density of like in the ocean, it might get a little more dense towards the bottom. It's not perfectly incompressible, but basically all liquids are incompressible. Also, steady motion, that just means that the velocity, the pressure, and the density at a particular point do not change with time. So if I'm looking at the flow of a fluid inside of a pipe, if I take a point in that fluid, I would say that the velocity, the pressure, and the density are always the same. Actually, the density is always the same anyway. But the velocity and the pressure are always the same at that point. Now, that doesn't mean that at other points the velocity and the pressure can't change. And in fact, we'll see that it does change depending upon the shape of the pipe. But at that point, the velocity and the pressure are always the same. The density is always the same regardless. The density will always remain the same because it's a what type of fluid? What tells us that the density always remains the same? And it's incompressible, right? That you can't compress it and give it a higher pressure, compressible. And then other is irrotational, and that just means there's no circular motion. Water in your toilet, ideal fluid. Is that an ideal fluid when you flush your toilet? Is it ideal? No, it's not. It's rotating like crazy. Okay, so no circular motion. So we're talking about flow of a fluid that is steady. It's a liquid, not a gas, and it doesn't move. It doesn't go in circles. And when we have an ideal fluid, and you need to know these four terms and sort of roughly what they mean, there are a couple of principles that come out of this. And the first is the equation of continuity. This is based on the law of conservation of matter, which we don't really cover, but you've probably heard it before. And that's just that in our world that we can't destroy or create matter out of nothing. That we have matter and we can change forms, but it doesn't come or go, just like we can't get rid of it. And so the equation of continuity, imagine a pipe. I have a pipe that's big on one end, and then it gets smaller on another end. The equation of continuity says that whatever material I put in to this end, whatever liquid I put in this end, I'm going to also get out on this end, the same amount. And we describe it by a flow rate. The volume flow rate is constant. The volume flow rate is a volume over time, right? Volume and rate. Rate should tell you that it's over time. So that's volume over time. This is equal to, I can think about a volume, and we've seen this before, as an area times a distance. Right, remember we were talking about the column of liquid over your head or the column of gas over your head? We talked about this has a certain area times the height, and that gives us the volume. Similar here, area times distance gives us volume. And then we divide that by time. But there's something that we've seen before. Distance over time, that's a measure of what? Velocity or speed. So the volume flow rate, V divided by T, is equal to the area times the velocity. All right, so we're going to talk about two different terms over here. We have the term A1, that's the cross-sectional area of our pipe. And then we also have V1, that's the speed of the pipe, or the speed of the fluid in the pipe. And then over here we have A2. And now we want to know what is V2. Just looking at that pipe that gets narrower, is that going to be a bigger speed or a smaller speed? Well, think about your water hose. Like, you have like little brothers when you were kids, or little sisters, even better. And you have a water hose, and what do you do with a water hose when you have a little? You do what? So in order to do what? To squirt them with the water hose, right? Or maybe you've had this done to you. And you put your finger over it. And when you put your finger over it, you're closing off part of the area. You're making the area of that hose smaller. So what are you going to make happen to the speed of the water coming out of the hose? It's going to go far. It's going to go faster, right? If I make area small, speed goes up. So V2 is going to be bigger That's what you're doing when you squirt somebody. When you put your thumb over the end of the hose, you're just changing the area of the hose, and then that makes the water come out faster because of this equation of continuity. So next time you squirt somebody with a hose, you say, hey, got you with the equation of continuity. Conservation of matter. All right, so let's see. The same volume of fluid must decrease, then the velocity must increase. When you squeeze the end of a garden hose, you decrease A, the area. Let me write the equation of continuity. We haven't actually written an equation, but the equation of continuity says that the volume flow rate remains the same. So the volume flow rate is area times speed. So A1 V1 is equal to A2 V2. That is the equation of continuity. That's on your equation sheet. But that says that the volume flow rate at point 1 is equal to the volume flow rate at point 2. And notice, for example, like with the garden hose, that if I make the area go down, then the speed goes up. If I make the area smaller, then the speed will go up. All right, let's look at Bernoulli's equation too. If the equation of continuity is based on the law of conservation of matter, actually, let's see. Yeah, no, this one, we'll do this here. So the Bernoulli's equation, if the equation of continuity is based on the law of conservation of what? Matter, right. The Bernoulli's equation is based on the law of conservation of energy, which is something that we've seen, that the energy at one point is equal to the energy at another point, that the energy is always the same. And we can sort of think of this, actually Bernoulli's equation is really the law of conservation of energy per volume. That in a certain volume of fluid, the energy always has to be the same. And so I can think of several different types of energy. I have kinetic energy, I have potential energy, and then if my fluid is doing work, I also have work. And so we sort of lump work in there. And then since really talking about per unit volume, energy always remains constant. This is a constant value. Then if I think of energy per unit volume, that's also going to remain constant. All right? That shouldn't surprise you too much, that the total amount of energy is constant. Also, the total amount of energy per unit volume remains constant too. So, 1/2 mv squared, that's kinetic energy, divided by volume, plus mgh, divided by volume, plus force times distance, divided by volume. And so what I get here is I get this mass over volume term right here, and a mass over volume term right here. What's that equal to? Mass over volume. That's density, right? So I can rewrite this then, and this will be the Bernoulli's equation. 1/2 rho v squared. Excuse me, that should be a lowercase v. 1/2 of the density times the speed squared. It looks a lot like the kinetic energy formula because it is. It's derived from that. Plus rho gh. Plus, and this is not so obvious, but if I have a distance over volume, remember we said, I'm going to put over here in a little thought bubble, as you remember back to the previous page, that volume is equal to area times distance, right? We're really doing dimensional analysis, but then I can remove those, and so that distance over volume is really a 1 over area, just looking at it dimensionally. And so that's force over area, but force over area, what is that? We've seen it before. Pressure. All right? So that's force over area. So that is Bernoulli's equation, it says that this whole thing has to remain constant all the time. Assuming that you're not doing any work on the substance, that this remains constant. So there are some sort of conceptual ideas that I want you to walk away from with this, and then also some calculations that we'll do. If V goes up, and this is sort of counterintuitive, but if V increases, what happens to your pressure? Now think back to the water hose that you're going to squirt your sibling or whoever with. You put your finger over it, that closes the area, makes it go faster. The water coming out, going at a faster rate, does it have more or less pressure than when it was inside the hose? What do y'all think? The pressure that comes out the end of the hose that squirts out, is the pressure of that water more or less than the pressure of the water inside the hose? Have you ever thought about that? You have? No.
I wish.
What are you thinking? You're right. But that's sort of counterintuitive because it seems like that water comes out at a higher pressure, right? Does it? Maybe it does. It's counterintuitive to me. But when you think about Bernoulli's equation, that if V goes up, the pressure is going to go down. Because if I make this value increase, then something has to give. That means that this value is going to decrease. Because the total amount of energy has to remain the same. So if V goes up, then the pressure goes down. So like for example in an artery, if you do the same thing, you put your thumb over part of it, or you fill it with something that's not supposed to be there, what's going to happen to the speed of the blood flow? Now blood isn't exactly an ideal fluid because it's not exactly non-viscous and there's some rotation that goes on, but it's pretty much an ideal fluid. What's going to happen to the speed of the blood when it goes through this constricted artery? Is it going to be bigger or smaller? It's going to speed up. Right, so here I have small v, and here I have big V. Because remember, A1V1 equals A2V2. If A2 is small, that means V2 is big. So I got a big speed in the fluid inside the artery. What happens to the pressure? Pressure decreases. So the pressure there decreases because the speed increases. That doesn't make sense though, right? Because you think of somebody with constricted arteries or in whatever way that they have low blood pressure or they have high blood pressure. Right, they get high blood pressure. But that's talking about their systemic pressure, right? But here we're talking about a localized pressure. The pressure at this point will actually get smaller. But you get a low pressure right here. So systemically, their whole body, and there's also some tests going on, but here you get a small pressure. You know what can happen if it gets too small? What happens to that artery? It does what? No. It'll collapse, right? Because you got a big pressure outside, small pressure inside, so it'll collapse down on itself. If the speed gets too big here, it'll just collapse down on itself. So low pressure, because the speed gets too big, that can lead to collapse of the artery. All right, let's do a problem. Let's see, I think we have one in the workbook we'll do. Yeah, let's do number 4. I'll help you with it. So I have 2 horizontal sections of tubing joined end to end. And in the first section, it's 10 square centimeters, 275 centimeters per second, that's the speed, and the pressure is this. In the second section, the area gets smaller. So let's first just draw a picture, right? First, is my pipe big or small at first? Big or small? It's big at first. It goes from 10 down to 2.5. So I'll draw a picture. Because the area is less by a factor of 4. So here my area is 10 square centimeters, and here my area is 2.5 square centimeters. So listen, I don't even look at the equation, because I know that my speed is going to be bigger in the second half, and it's going to be bigger by what factor? A factor of 4. Right, so I can just say, if I want to know the speed, I multiply this number by 4. But if I want to go through the procedure, then I would say, well, I have A1 V1 equals A2 V2. That's 10 square centimeters, 275 centimeters per second. Notice that I'm not converting my units. I don't have to do that here. However, when you're using Bernoulli's equation, you do have to convert to SI units because you have these embedded units. You have newtons and stuff embedded, and those use SI units. That's equal to 2.5 square centimeters times V2. And then we solve this for V2, which is going to be equal to 10 over 2.5, which is 4, times 275. That's 800, 1,080. 1,100? Is that right? 1,100 meters per second. Excuse me, centimeters per second. Okay? So that's the first part. That's the equation of continuity. But now I also want to know what is the pressure. So what is the pressure equal to in this smaller pipe? And in order to do that, I would use my Bernoulli's equation. I would say 1/2 rho v squared plus p is equal to 1/2 rho v squared plus p. All right, let's put some subscripts here. 1, 1, 2, 2. Notice I left a term out. Why did I leave that term out? I left the rho gh term out. What do you think? Sorta. Chris, what do you say? Right, because it's constant. Both of you are right. That h, because it's a horizontal tube, h is the same for both. And so I could write them in, but they would just cancel out. Okay? All right, so here I want to know, I'm looking for P2. I know everything else. I know the density, and I know the speed, and I just need to find the pressure. Let's see, can you do this? I'm not going to do it here. You have to convert all of your units to SI units. I wouldn't make you do that on the test. But you have to convert all those centimeters and grams to kilograms and cubic meters. So solve for P2. And make sure you convert to SI units. That's kind of a hard part in these last few chapters, is that sometimes I tell you we have to use SI units, and other times I tell you that you don't have to use SI units. So let's just look at this and think about, why is this an equation where I have to use SI units, whereas this one wasn't an equation where I had to use SI units. Y'all see the difference in the two, why one requires SI and one does not? The reason has to do with this term, because this term is a pressure, and this pressure is measured in pascals, or newtons per square meter. And so this has embedded SI units. This unit of this term is made up of kilograms and meters and seconds. Okay? So you can't then have kilograms and meters where you have grams and centimeters over here. So when you come to a problem, you want to ask yourself, am I mixing up my units? And if you are, then you need to use SI units all throughout. Whereas this one, my units, they don't mix up. Like I'm using centimeter squared over here and centimeter squared over here, so everything's okay. And centimeters per second here and centimeters per second here. But you can't do this. You can't use centimeters per cubic, or excuse me, grams per cubic centimeter here, and then newtons here, because then you're adding two dissimilar units. Yeah, look excited. Sort of. All right, you'll get the feel for that. Let's go back and do this clicker question. Where is the pressure the greatest? At point A, point B, or point C? You ever seen a standpipe? A standpipe, if you have a pipe with fluid flowing through it, you can have a standpipe. It's just a pipe that comes up out of the top of the pipe that you can determine what the pressure of the fluid inside the pipe is. So where is the pressure, A, B, or C? Where is the pressure the greatest? Or are they all the same? Oh, yeah. Oh, no, don't look at those lines. These ones right here. No, that was just, sorry, that's like those. All right, let's stop in about 10 seconds. Stop at 117. Oh, you're what? Evenly split. Okay, it is either A or C. Look, you remember when we were talking about with the manometer? If we were looking at a manometer, would a greater column, a taller column of liquid, would that denote a smaller pressure or a bigger pressure? Bigger pressure, right? With a manometer or a barometer, even better as an idea. Think about, I have this tube, I have liquid here, I have a pressure that's pushing down, and it pushes this liquid up in here. The taller this column of liquid, the bigger the pressure that's pushing down, right? So the one with the bigger column is the one with the bigger pressure. So there's a pressure here, and a pressure here. This one is the biggest pressure, this one's the next biggest, and then this one's the smallest. And it's all dependent upon the height of that column. That the pressure here is rho GH. And here it's also rho GH, where H is less. And here H is even less. So the height of the column, it works a lot like the manometer or the barometer, that by the height of the column I can figure out what is the pressure. And that's what we use standpipes for, to figure out what is the pressure of the fluid inside of the pipe. So the pressure is greatest in A. Now this is interesting. Y'all think about this. I like this question. So we've already stated that the pressure on the left is biggest and on the right is smaller. So what is happening to the pipe? Let me show you in color. You might not understand the question. So does the pipe narrow from left to right? That is A. Ooh, goodness. This would be A. It narrows from left to right. Does the pipe get wider from left to right? This would be B. Does it have a constant cross-sectional area? That's C. I'm drawing the bottom of the pipe. Y'all get what I'm doing? Drawing the bottom of the pipe. Or is it none of those? Is it A, B, or C? Which is it doing? All right, I'm going to stop at 140, okay? 140. Okay, let's see. So if I have a big pressure, does that mean my speed is big or small? Small speed means big pressure. So I want a small speed down here, small v, and big V over here. And in order to give me a small speed, does the pipe need to be big or small? It needs to be big. So that's the blue line. A is right. Oh, I didn't know I could do that. Look at that. Okay? Because I have a big pressure here. By Bernoulli's principle, if my pressure is big, I must have a small speed. Here, my pressure is small, so I have a big speed. In order to have a small to big, I have to get smaller. Like putting your thumb over the end of the hose. Okay? All right, I think we have a few more concept test questions in the back. Have we done any of these, actually? We haven't done any of them? Oh, man. Are you sure? Just this one? Okay. Can we do this one? Okay, let's try this. How many of these do I have? Oh, goodness, we have a bunch of these. I might turn some of these down. We'll just do it here. All right, let's stop at 1:05. 1 minute. 1 minute. Okay, good. E is right. You want to lie down flat. That's useful information to know. Like if you're ever out in the bayou and it's frozen over and you find yourself in the middle of it. This is like out of your mouth, you let a small bubble there. All right, let's stop at 30. I'll stop at 38. Okay, very good. C is right. Let's see. How do you make a witch itch? How do you make a witch itch? Take away the W. Okay.